Welcome back to lecture 12 and 13 of the GIAN course on adsorption for techniques for carbon dioxide capture, modeling and simulation insights. Today, Dr. Debanshu will discuss about modeling and economic analysis and the types of solid gas contactors for carbon dioxide capture. Please continue.
Okay, yep, very good, thank you. Where is the point? Oh. All right, okay. Good morning, everybody, and we are on our last day, so we had a very good discussion about mainly on the axial flow type of the contactors. But as I keep saying, that one of the big differences between the liquid gas systems versus the solid gas system is that the type of the contactor makes actually a lot of difference. So in terms of the limiting performance that which we would like to achieve is what you are getting from the isotherm. But the issue is that it's very difficult to get close to the isotherm. So as we know, like in a typical, I'm just always trying to draw analogy with respect to the liquid gas systems, which we are all familiar, like a distillation tower, right? In a distillation tower, what is the best efficiency that we are trying to can achieve? It's close to the vapor-liquid equilibrium, right? But in reality, we cannot actually achieve close to the vapor-liquid equilibrium because of mass transfer resistances and other reasons. That's why we go to a non-equilibrium stage model to capture the distillation tower. What is the parallel of that for the solid gas contactor? It's much more difficult than even liquid systems. It's because of there are a lot of things which we do not currently understand in terms of the mechanism for the mass transport, heat transfer, kinetics, and all of that. And those things, the purpose of all these different type of contactors is basically get rid of those limitations. So always the point to keep in mind is that only thing that we are trying to do by designing this contactor is taking us closer to the isotherm. Whatever is the isotherm that you got, or based on the thermodynamics, whatever you got, the maximum loading, no matter what you do, you cannot exceed that, because that's the thermodynamics is actually the upper bound that you can ever achieve. So always keep that in mind. I'm not saying that by doing this, you will be increasing or loading and all of that. No, you are limited by your isotherm, but we want to get closest to the isotherm. That's what we want to do. So the many different types that actually do exist, and they bring their advantages and disadvantages. So one of the type is the radial flow type. So whatever we considered before is the axial flow type, which is very obvious and the very common design and all of that. But one is the radial flow type. So this is a typical axial flow type. So where you simply think about is the flue gas coming in and this gas goes out. The problem, as we are discussing here, the cross-sectional area is constant. It does not change with the length. And so as a result of that, if you keep increasing the length, then there will be more and more pressure drop through these systems. The issue with the flue gas is that there is so much amount of nitrogen present there that you do not want to really compress that gas really. Always try to avoid if you can, because that's actually massive amount of compression power, right? So radial flow bed looks like this, right? What you do is that it comes through the inner annulus, and there is an outer annulus here. So flue gas comes in and then moves this way, goes out. So this could be one configuration. And then it can also be that the gas will come in at the outer annulus and then flow this way. So it could be either type of configuration is possible. Then if you look into these red arrows are actually considering that what is the hot stream or the desorption. So the blue one is for the adsorption step, and the red one shows you desorption step. So now if I say this is a counter current desorption, so it is possible that the flue gas comes in through inner annulus. If it goes this way, then the counter current basically means that the steam or whatever hot gas that comes in, that actually comes through the outer annulus. So it will be counter current, right? And it could be other way around. It is possible that the flue gas, instead of inner annulus, it comes in the outer annulus. So if it comes in at the outer annulus for a counter current configuration, then the steam or any hot gas will be flowing through the inner annulus. When we consider the co-current desorption, right, that what happens is that you can consider that both the gas and the steam flows in the same direction. So flue gas can come in the inner annulus. In that case, steam will come in the inner annulus, or the other way around, that both steam and the flue gas both comes in the outer annulus. What is the best configuration? We don't know. This depends on the flue gas CO2 concentration that you are processing, and what is the extent of capture that you consider. In general, when you actually consider the typical PSA process, PSA, TSA, vacuum, swing, any of these, the flow rates are actually counter current. And one of the things is because of the cross-sectional area, that what you do not want that CO2 to get reabsorbed. I had this discussion with some of you yesterday, but that is one of the things that happens there, but this is not the case over here. So just to ensure, I think that was a very important point, that let's see whether we realize it. And when you simulate desorption, you will see this. For example, if I have a fixed bed and assume that my feed flue gas in is this direction and goes out. Assume this is the case. I do know, like somebody, let me draw it the other way around. I know that in reality, because of the flow rate, it generally tries to flow other way around. So assume this is the flue gas in, and this is the flue gas out. Now, what happens is this section of the bed, if I'm doing the loading, so this is 0, this is 1, this is a normalized length. And if you look into the loading 0 to 1, what you will find that the loading is something like this. So later sections do not really capture anything. Now, when you start desorbing it, say if I'm actually trying to desorb it this direction, so I say steam in or whatever, and then I say CO2 out. If I have a configuration like that, what would happen is that steam desorbs the CO2, because this portion is very high CO2 loading. The moment the CO2 goes desorbed, it has got very high partial pressure of CO2. That CO2 can actually adsorb here. Remember, this section did not adsorb anything here, because when you actually treated the flue gas, that only had maybe 5 to 15% CO2 concentration. And by the time it reached here, it was very low, maybe 1%, maybe ppm level. But when you are actually desorbing the CO2 from here, and it is in presence of steam, this CO2 concentration may be 50%, 60%, 70%. Under that condition, then it will adsorb here. So basically, we are desorbing from one section, adsorbing in another section. And that is mathematically makes sense. In real life also, these observations are done. Now, the problem that comes there is that you are not really desorbing the bed, because this is readsorbing here. So for completing your desorption cycle, you have to keep passing the steam that you desorb from here, then you desorb from here, then you have to finally desorb from here. So that's one of the reasons that these configurations are actually always done in the opposite direction. So in that case, steam goes here, and then when it dissolves, this concentrated gas goes out. So it's a traditional thing. Yeah, I actually now, yeah, I should have actually talked about that before. There is, I forgot to mention, please, the book by Professor Ruthven. This is adsorption, I think it's called adsorption processes or whatever. That book is, if you really see, I think it's adsorption processes. I have to check exactly the name, but it goes by adsorption. And this is, even today, this book is very dated, but this is, in my view, still the best book, that if you read this book, you will actually learn everything about adsorption. He talks about the practicality, theory, thermodynamics, everything that book's covered there. It has got actually a lot of good discussion about this configuration also. Like it goes about the practicality, what happens, and you can see this in your model too. Okay, I diverted a bit, but the point I wanted to make that this thing is not necessarily true for the radial flow configurations. All of the discussions in this book or any other places are for axial flow configuration. The radial flow configurations, you may do co-current, you may do counter current, and it may not be an issue at all. So like for example, if I actually do a co-current desorption here, that means that the gas comes in here. The main, why it may not actually, when you desorb it, why it may not adsorb here is because this cross-sectional area is very small. So the gas actually speed up through the process. It's a very high velocity. If you simulate this bed there, and depending upon the annular size, it can actually speed up by 100 times, 1,000 times through that locations. But it's a very short path length, and because of a very low residence time, it actually has got no time to get recaptured. So many of these observations do not hold for the radial flow bed, okay? And it also gives you one more degrees of freedom, which we love always as a process systems engineers, right? Like this is my optimization variable. In axial flow bed, these are the only two options that I have, co-current, counter-current. Here, I could consider all type of configurations. Like you saw all these four options, these are possible. Here, I just have got only two options. So instead of two, I have got four superstructure to evaluate, and one of them may be optimal. So how do we model this? Well, we consider radial flow bed, the similar models, but unfortunately, Aspen, the AdSim will not be sufficient to do that. So this is basically almost what are the equations in AdSim. We recreated this, so coded all of those things in Aspen custom modeler, and then do that. So without spending too much of a time, what I would like to show here is that we tried to compare that what happens with the same jorbent if I have got a radial flow bed versus axial flow bed. And the idea here is that what we wanted to do is that we consider this, see this design looks very different, but the idea is that we wanted to have a same bed volume, same bed solid volume. So basically meaning that I have got X kg absorbent. I have two options. I can put it in an axial flow bed. I have also the option of putting it in the radial flow bed. So for the radial flow bed, this is actually the solids hold up. Axial flow bed, this is a solid holdup. So those dimensions that you have here, that makes the solid loading the same. So question is, which gives me better utilization of the solid, right? So that's the whole idea. Now, what the interesting thing is, first, as I say, pressure drop. So you see, if you look into axial flow, irrespective of whether you consider co or counter current configuration, and with respect to the time, you will see that this is how it actually shows up. But look into the radial flow bed actually. It's way low. Even though this looks like not a very big pressure difference, but when you actually consider the flue gas and consider the massive amount of the flue gas flow rate, there is a big difference in the power requirement based on this pressure drop. So you generally try to keep it very small. So this is very big differences here. What you might like to think about that why this is like this, anybody can guess. It comes here, increases it, and then shoots. Okay. So you saw that configurations, right? The pressure drop comes there, and for both cases, after some times it shoots up, and then it comes down. Anybody can guess why the pressure drop is lower, then it increases, then shoots up, and then decreases again? For any type of bed, it is showing this same type of a profile.
When CO2 is getting absorbed, it's blocked in the passage, and it increases the pressure drop. After a certain limit, there may be some cleaning or more force, then again getting
Right. So up to here, so basically at this point, we are capturing the CO2. Because I am capturing the CO2, the flue gas flow rate is lowered. So the less amount of flue gas is flowing through the system. As it is absorbing less, or the CO2 has to go through a longer path length, the pressure drops keeps increasing. Up to this is adsorption cycle. This is actually desorption. So this shoot up is because of the desorption. So the moment you go to the desorption step, it is shooting up because when you introduce the steam there, it is releasing that CO2. So large amount of the CO2 and plus steam that will actually now flow through the system. So that gives the shoot up, and then it decreases because the CO2 is getting desorbed. So there is not much CO2 coming out from the bed that needs to flow. It is basically only the steam that is flowing through the system. So that is what is actually happening through this whole entire process. So interesting, if you simulate this entire cycle, this pressure drop shows some interesting dynamics, and that is why it is doing. But nevertheless, there is a big difference in those two things. Velocity, this is an interesting observation also. You notice that for the axial flow bed, this is the velocity here, but for the radial flow bed, with respect to the length, there is a very big difference in terms of what you find in terms of the velocity. So this is actually near the outer annulus, as you will be expecting, and then it can actually speed up, okay? And then you will see that the residence time, which goes by the local residence time, obviously, as you will expect, the axial flow local residence time is pretty much flat. And here, what happens is that obviously, as you would be expecting, that the residence time will keep increasing. That corresponds to this velocity, actually. So this can actually help you to give you better absorption. Now, the thing which I was actually kind of always keep saying is that this is all what we did for a commercial scale design. Notice the residence time actually. This is in seconds. So commercial scale reactor, like if you go to like any typical industry, petroleum, petrochemicals, cryogenic and anything, calculate the residence time can be second, milliseconds, 2 seconds, 1 second, 3 seconds. So that basically means that your kinetics has to be very fast. Without that, basically you are saying, I need an ocean of solids if my kinetics is very slow. So that is what is basically it shows you. So a couple of interesting things here. This shows you all the breakthrough at different locations. And so this is adsorption, this is desorption, this is adsorption, desorption. So all of those. And now, without going into these profiles too much into it, the interesting thing here is at the breakthrough, if you do a loading profile, you see the average loading profile is this. 0.75, and for the radial flow, we got somewhat higher average loading. This is using the same jaw band. What is the maximum for these ones? Was about 2.25 under these conditions. So you see, even though we increase, we are not there. So this is the main thing. When you actually do the design, and sometimes in the laboratory scale, we keep doing a lot of things, say, oh, improve the isotherm. The reality is, you may not in many cases really be too worried about the isotherm, because you will not realize that anyway. So this is, you see this, even axial flow, radial flow, both are so far from what I would have gotten in an ideal scenario of 2.2 or so for this particular material. And this shows you the temperature profile, and this is adsorption cycle, this is the desorption cycle. As you will see, it comes here, and because in the desorption, the temperature goes up. And so all nonlinearity is there. I would say that like these cases, that cycle setup and whatever I was showing you guys yesterday, adsorption, desorption, this we had to code it ourselves. The other issue that comes there is because of the flipping of the direction for the co-current and counter current, it's actually very tricky how you start the desorption. Because you start the adsorption and then you are basically saying the flow is not in this direction, flow is in this direction. So the sign of the velocity actually changes. Typically, anybody who works in the area of CFD, you are very well aware of it. Like in a typical CFD simulator, they can actually handle the change sign of the velocity. It is very difficult to do this in Aspen or any other simulator because it will change from plus to minus. That is what it changes. The other thing is the composition changes. So what we do there is, just to give you a quick glimpse, this is a little complicated here. So at the end of the adsorption, we take a snap, then keep the snap some other place, and then when you do the desorption, we load the snap along with this loading. So we change everything, all the directions and other things. So there is a script we have to write to simulate this type of cycles actually. This is not, you cannot change in Aspen, you cannot change, like in AdSim, you cannot change the direction actually. All these things. So like basically you cannot say that I have these co-current at the time and the other side is actually moves from the other side. That is not possible. So those you have to write the script that ACM will solve it. This is still ACM. It will still solve it, but their AdSim model itself is not set up for doing that.
So Aspen doesn't consider velocity as a vector. It doesn't consider it just like a scalar.
The way we declare that, it really depends upon how you do this. So if you see this, if you see these codes, we say that velocity as distribution 1D. If you declare this velocity as a distribution 1D, it is a vector. It depends upon how you do it actually, but these are all treated as a vector. So remember when I was writing these equations in this, again from BSL, d dx u ci, right, that term. So u and ci both is a function of the derivative. So there's u and c both are distributed variables. Yeah, so it's a issue is more from a numerical perspective. So Newton solver has got issues. Most of the Newton solver has got issues. If you are worked in this area of optimizations, you know how do we trick all those things. Like remember that all the slack variables in linear programming, if anybody has even done a linear programming classes, you know that how we handle the slack variables and keep things positive and switch things around. So internally the solver does it. If you put it externally, the problem is going over zero. So you have a plus, when you try to go to the negative, you have to go over the zero. There is many of these things become ill-posed when you try to go over zero. That's really the issue. So what we do is we do not let it go through that. We basically directly jump from plus to the minus side. So we just flip it ourselves through a script. This is possible in Aspen, but that script actually, it took us some time to develop. Like one of my students, Gautam Kotam Reddy, he developed the first one, and then we kept updating that one. So that, but it's not there as part of AdSim. Yes, yeah.
So you have to specify the weight characteristics in the Aspen axis, right?
So as I was saying, that the main thing here is that those valve and other things that you set it up there, that is only for your axial flow bed that it will actually do that, right? Axial flow bed has got only two options. So you have got the co-current, like both this way, and then you can say it is coming countercurrent. Here it has got the other way around. Like the issue there with this that actually comes there is that you can have counter, and it can be both inner and outer. So this gives you actually many more options there, and that is at one point of time this velocity becomes negative. But remember, in Aspen's case, so okay, just to ensure that we are on the same page here, so it depends upon which direction you consider as a positive R. So this is R direction, right? Which consider your positive R. The moment you do that, it could be plus R, minus R, minus R, plus R, minus R, or minus R, plus R. Those things, those switching becomes actually difficult. Yeah. So, but that you can write the code to do that. Okay. So yeah, it's a little tricky, but you can do it. But we found some interesting results here that what we wanted to do. And I'd say that if you now what happens is that if you can, so why now I go to some interesting thing here. Remember what I actually told before is that we wanted to go like whatever, like 2.23 and whatever. And if we now actually go to a very high average loading, then you have to do some kind of a heat removal. So this is considering an ideal isothermal scenario, which it is not practical, right? So this is the point you have to remember here. So what we did here is, now the tricky thing is that for the fixed bed, axial flow fixed bed, these heater design and others are generally people have looked into it, and it can be done. When you look into radial flow, this may be a little bit challenging conceptually, that how to do it. So we actually thought about some options. I'm sure there could be other options that people can actually think about. But one of the configurations that which we are saying is that it is fed through like a ring actually. So it's a pipe that goes through, this is a distribution pipe, and this is through a ring. So this is in, and then it distributes it, and it collects it and take it outside. So that was one configuration that we consider there. And then also, obviously, you can consider co-current or the counter current configuration. This is completely conceptual. But what it basically says that if you don't do heat removal, there is not much benefit that you can get from these systems, right? So when we do this without heat exchange, you see 0.2, 0.85. With heat exchanger, we can do 2.84. Yeah, this one actually probably was 3 point something, right? Yeah, this is a modified metal organic framework. So this was about 3 mole or so average loading. And in this case, this average loading which we got is about 2.84, that which you could get. And then you see the cycle time and everything really goes up. Okay. The other interesting thing is you see the desorption time, if you think about it, is also depending upon, if you use an heat exchanger there, your desorption time actually also goes down quite a bit. Like if you do not do it, you have to put the steam and it just keeps flowing and flowing, and you are not able to provide the heat there. But with this gives you the opportunity. You see that how these lines actually looks, how squiggly this is, like these are all very nonlinear. So that is where I was saying that if you just try to do it straightforward like this, it seems like a nice concept, but if you look into it mathematically, this is very challenging. One is because of the flow direction. Second is basically the moment your flow direction changes, you have to say, how do I pass on the loading at the end of the adsorption to the end of the beginning, end of the desorption to the beginning of adsorption. So how I do that. Then the third thing comes there is because of the stiffnesses that actually arises here. The solver will absolutely run into trouble. So for all of these cases, when you actually do it yourself, you have to do two things that which I discussed before. Equation scaling, variable scaling is absolutely critical. Without that, you will not be able to converge this. You have to also go by each equation one at a time and say, is it well conditioned, is it well posed, under what conditions it can actually degenerate, and all of that thing. So this is definitely a challenging problem, but it can be done. When AspenTech, the solvers, has got all of these things, but you have to kind of help it up. Then the next thing was that same way which consider commercial scale up, right? This is something, this is a concept that I wanted to bring it here. The breakthrough time concept that you see in a typical adsorption cycle people consider is not necessarily the breakthrough time concept for CO2 capture. So what is a breakthrough, right? So if you go back to the very fundamental question is, what is the breakthrough condition? So if I plot this and say C over C naught, and this is with respect to time, and you may say, well, this goes to 1. You may say, for my system, this is the breakthrough. It may be breakthrough here for another one. So maybe for one system, this may be for another system. It depends upon what is the tolerance of these in your systems. Like if you are doing a cryogenic air separation, this is how you should be defining it. Like, because if your CO2 goes through the system, you will be saying, no, I cannot accept it, because it will be forming dry ice later on, so I cannot accept it here. But when you are doing the CO2 capture processes, it's different. Because if you are targeting the 90% capture or 95% capture, remember, during this time, you have 100% capture. So you need a time average 90% as the breakthrough. So for CO2 capture, it should be really the area under the curve. You have to take the area under the curve, and you have to basically say, when this integral area under the curve exceeds whatever is the limit, that is when the breakthrough takes place, right? Because when you're sending it to the pipeline, you are saying, I want 90% capture, but I'm doing 100%, 100%, 100%. So I can afford to do only 80% capture or maybe 85% capture. On a time average basis, as long as I can do 90%, I'm fine. So this is the difference in the breakthrough definitions. This is what we defined as a breakthrough for most of our papers, that it's an integral value. That is what we are trying to do, okay? Okay. I know many of you are interested in the cost, and as you are talking with me, I thought I will give you a quick glimpse of what is the other side. And in the beginning also, I kind of said that cost is, ultimately it's a dollar value or a India INR value that is probably the most important thing that you are looking into to be competitive in the market, or for somebody, your management or any other client that you go to say, my technology makes sense. So how do I convert all of these things into a cost? The bigger problem here is that it's a dynamic problem. So we have done cost analysis as part of our undergraduate courses, like design courses, but those are mainly for steady state system. So here we need to draw the parallel for that, and there are many different ways to do this one. You can do NPV analysis. You can also do equivalent annual operating cost analysis, and this is the typical definition. This definition is from really from our book, directly from our design book that you can actually follow there. And all of these things, many of the things that I will be talking about is basically from our design book. We also can use the Aspen Process Economic Analyzer. It will not do it basically for the adsorption systems because this is not a steady state system, but it will do it for everything else. I'm not sure if has any of you have used Aspen Process Economic Analyzer? Okay, this actually has got a database from all over the world. Like US Gulf Coast is probably, they have the massive amount of the data that they collect every 6 months and populate it there, but it is also there in many continents. I do know in India, multiple regions they have the databases. So they actually get the data from the vendor for the general formulations. I'm not sure any of you have used the software that goes with our book, like the cap cost. No, right? So yeah, this goes with the book analysis, synthesis, and design of chemical processes. Yeah, this is Professor Tartan is the first author, then Sewiz is the second author, and I'm the third author here. So this book is, if you look into the 5th edition of it, if you go to there, it will show you this software is free actually, but it will give you a capital cost estimation and all of this. Most of the leading equipment cost and the cost databases and equations, correlations are all part of it. It's Excel based, and it will give you some warning about the VBA. Just accept that one because it's all coded in VBA. So, but this is a free software. So if you, and pretty intuitive and easy, it will give you NPV analysis, it will give you EAOC analysis, and if you have your cost, you can just type it in. There is a place called user, and other standard equipment items is there. APEA is more sophisticated because they keep collecting data from real life, from the vendors, and so there is probably more accurate here. And we do update this based on, but not so frequently because these are commercial, and this goes with our design book really. So, but the point I wanted to say is that this is how you do the costing. Now you cost everything else, and all of those things we like to compare. So let's see what we find here. So the same absorbent that you kind of see here is that we found the co-current configuration is the most optimal. That is interesting, and I'm sure you cannot read it because I cannot read it from here myself. This rotation here. This number is low. Let me read it for you. This is 227.6. This is 270.4. Remember, this is a cost. So cost lower basically means is that this is more economic. So it is showing basically the co-current configuration is actually more economic than your overall system. The interesting thing is that what we found that the number of bed here you see, like we had got, if you're considering an axial flow bed for the same amount of flue gas configurations, where you needed 64 bed here for that cases, and here we could just require only 34 bed. So that's one advantage that you have there, and then also the steam cost also goes down. And you see that instead of counter current, the co-current was optimal. I'm not showing the results here for all of those, but in that we have a paper here that you can compare it. But this is an interesting concept without doing any fancy stuff. If you have the vessel, put it into 2 annulus form, and then you can actually have a radial flow configuration. Okay? Any question anybody has? And yeah, we of course compared with MEA, and compared to MEA, there was a reduction as well, actually.
What is there a comparison between co-current
Yeah.
and counter
Yeah, it's actually in the paper. So all the details, economic calculation, numbers, everything, and all those details. I have a list of all the papers that corresponding to everything that I will discuss. So you can see all the breakdown. All the equations are there, how the code and how it was solved, all the numbers, everything is there. Yeah. Okay, I will now actually say that what we found, that if we go by the counter current versus co-current and we consider some optimization with respect to the flue gas residence time. So flue gas residence time basically means how much flow a single bed can handle. This is not obvious. I give you a design like say 5 meter by 10 meter. Question now comes is how much flow should I get through it? It is arbitrary, right? But there is an optimal. If you send, I'll be very slow, so let's ensure that we listen carefully here. If I give you a bed of a fixed size or fixed dimension, if you send less flow through that bed, I need more number of parallel bed in adsorption because I have to handle so much amount of flue gas. The amount of gas that I need to handle is constant. So through a single bed, if I send less, I need more number of parallel beds, right? However, a bed will be in line for longer time, right? Obviously. If I send the large amount of the flow rate through a bed, number of beds will go down. However, the breakthrough will happen fast. So my cycle time will be less. So in one case, if I have a breakthrough in 30 minutes, if I'm sending more flow, it may break through in 5 minutes. The moment it breaks through, you have to go to desorption cycle. The moment it goes to the desorption cycle, there are two penalties. Remember I discussed that. The desorption heat, you have to think about it. One is the sensible heat. Every time you heat the bed, that heat for heating up the solids is a penalty that you incur. So desorption heat is equal to heat sensible heat for heating up the adsorbent plus bed plus heat loss through outgoing gas plus heat of desorption plus any other heat loss, right? So this one, it doesn't matter. Whether I have a cycle time faster or slower, it doesn't matter. So much amount of CO2 I have to desorb. So this is constant. But every time you get into the cycle, this adsorbent flow rate is something that you, oops. Oh, okay. Okay, so we can continue the discussion here and you can load. So basically what happens is that this sensible heat is the one that you incur the loss. So you see, this is a trade-off. So slow flow has got larger number of bed, but lower penalty for the sensible heat. Faster flow rate has got lesser number of bed, but you have got a higher penalty because of heating up the bed. So there is a trade-off between capital cost and the operating cost. So that is where there is an optima, okay? So I'll say trade-off between capex and opex as you change the residence time in the bed, that is flue gas flow rate through a single bed. So this is the main thing that we have to keep in mind here. Okay. So yeah, this is an optimization variable that which we really wanted to look into as part of this overall thing there. Okay. So now this kind of actually gives you an idea about the radial flow bed. I have got some other materials for the radial flow bed, but I probably should change gear here. Any questions anybody has for the radial flow bed? Okay, so if not, you can go 2 slides back, but I can take care of it. Yeah, so now I'll be switching the gear here. Another good idea is actually the rotary packed bed. This is the one thing with the rotary packed bed is that basically the idea is very simple. It looks like a fan. So think about your household fan, but it's like a gigantic blade, and it is all full of adsorption. One section is for adsorption, another section is for the desorption. This draws parallel to power plant air preheater. If you go to an existing power plant, even now most of the power plant air preheaters are like that. So if you see this, we call it a Langston type air preheater, right? So I will say that if you just want to read about the typical design that we have, it's a LJUNG Storm type air preheater in coal-fired power plants. Very traditional, but the idea here is that the bed, so we have got different sections. So this is how the bed looks like, and this is an axis that actually over which there is the motor that actually rotates it. You can have adsorption, desorption. This is a design. So you can say, like, I want 70% for adsorption, 10% for purging, 20% for desorption, or whatever, right? So you can segment it. And like if you look into power plant air preheater, there are 3 sections. So there are also some cases there are 2, but most modern one has got 3 sections there. So primary, secondary for the tertiary air, and you could have the different air preheater sections. So that way you can actually segmentize it, and these guys have come up with their seal design and all of that to ensure that there is no leakage there. What is the advantage of this? One of the big advantages of this is that the way to understand this system is that because you are able to rotate the bed, you are changing the residence time of the solid. In a fixed bed, if you are changing the flow rate of the gas, you are only changing the residence time of the gas. Solid is staying there. In this case, because I can rotate it faster or slower, I have another degrees of freedom. So I can take the same bed, I have got a lesser amount of gas that I need to process, I will just slow down the bed. And I want to process higher flow rate, I have to rotate it faster, of course with the understanding that I'm able to heat it up and dissolve it, and those limitations are there, but you have got lot of cushion there. This may even be good for a laboratory scale, like if you develop a small one of these, like you say, in my lab I could only synthesize 1 gram of the adsorbent, and now somebody comes to me and say, yeah, you need to process bunch of CO2 concentration like 5%, 10%, 15%, 30%, and all of that. That 1 gram of adsorbent may be insufficient for you to do that. And you basically say, okay, I need to do 20 gram or 50 gram or 100 gram of adsorbent, and it may take longer time, but this gives you a flexibility that you can just speed of the motor, and that gives you the residence time, and then you can process more amount of gases. So this has got one really nice degrees of freedom. There are many different ways to do this. One is the consideration of the heating and the cooling, and there is a static heat exchanger tubes that we actually anticipated in between 2 layers for heating and the cooling. Okay, so without spending too much time into it, this I already explained before. Like this is a tetramine appended MOF that which we evaluated for this one. Okay, and I will skip these ones. So this is basically the main thing that you have to really think about for one of these is that for the solid there is a theta direction. So again, if you want to use straightforward Aspen AdSim, it will not work because there is no theta direction there because it's rotating, right? I do know some people try to use it for modeling it, but it's a big approximation. You have to make what is happening for the solid as it is moving there. So there are 3 directions it is important: theta, R, Z, all of that. So we mainly consider the Z and the theta and assume that in the R direction it's not much, but you can incorporate R direction as well. So this is all the derivations, we did this, and now without going into the equations much, this is we basically for the non-reactive systems we wanted to show how it actually looks like, and this is for air preheater, and we showed that for a non-reactive systems the prediction from our model whether it compares well with the actual power plant data or not. So this is what we found. Seems like it was pretty good. That's what you will see, that these temperatures are for air and the flue gas, because in power plants they heat air by using the flue gas, and this is only a heat exchange problem, no reaction here. But this is the only data we could find in the literature that we could utilize it. Okay. Then what we did was that we take this and we solve an optimization problem. This model we have coded in multiple softwares depending on some of the issues that which we kept facing. So we had Aspen custom modeler, and because the problem with this guy is, this is actually also a tricky problem. So when it is coming, say this is the adsorption side, okay, say this is the adsorption side. What is the, so for this, because the solid is moving, I need to have a boundary condition for the solid. What is the boundary for the solid? Whatever comes out from here. What comes out from here depends upon what comes out from here. So you see, it's a rotary boundary continuity that you have to consider here. So this place depends on this place depends on this place, this depends on this one, and so you have to consider that. So it's a tricky boundary condition problem that you have to solve. And there are multiple different ways we did this. We created initial gas by, in SEM we had difficulty in solving this, so we first did a dynamic problem. We said we start out with something and let's solve a dynamic problem that generates an initial, good initial gas. When the dynamics settle down, that means these boundaries has settled down. Then you grab that snapshot and load it as a steady state, and then you design this. So in Aspen, this is what we did. But this could be done in Python. Even IPOft that I was saying, we had difficulty in solving these optimization problem. So this solution is used by using CANopt, actually. So CANopt and within Python framework. So most of these things I will show you this, and these are the decision variables, right? Okay, all right. Yeah, we did it, considered it like a polishing step. This polishing step basically means is that it's a hybrid capture. So it's a solvent adsorbent. So I know there was all this consideration that we are saying sorbent membrane, solvent, sorbent, all these hybrids possible, right? So this one actually considers a solvent sorbent type where this guy is doing a polishing step. That basically meaning is that 90% here and the solvent captures also around another 90%. That means it gives you a 99% overall or even 99.5%. So you are entering the direct air capture range. So all of those configurations possible. Okay, yeah, this gives you all the optimization, the Pareto front, show the energy requirement for each one of them. And yeah, these are, you can see that this stiffness is, many solvers will struggle actually to do this optimization problem because of all these stiffnesses. You see actually it almost looks like a vertically going up and then comes down. So yeah, so we see they are definitely challenging problems to solve, but believe me, this can be solved. So before I go there, again, this paper, we have got a lot of details there. We are just submitting it for publication, not published yet. But yeah, it should see the light of the day pretty soon, actually. So, this is, I would like to say that these rotary bed are tricky problems because of the changing boundary condition and continuity of the boundary that you must satisfy, and generating the initial gas for such boundary condition is very difficult actually. So there are tricks to solve. This is actually in the CFD literature, people do it, all of these things routinely, like they always try to solve a dynamic problem there, right? With our cases, we generally in systems, we try to solve a steady state problem. Rotary bed is steady state. It can be operated at steady state. But under steady state, this individual boundary conditions, what it should be, is very difficult for anybody to guess. So you can, as I said, that just like other cases, you can solve a dynamic problem. Dynamic problem will converge. So it might take you like 2 hours or 3 hours for converging the dynamic problem. When you see that everything settled down, take a snapshot, use that snapshot for steady state, and then you can solve for steady state. Okay, any question here? Yes, it is partitioned, yes.
And so it has to be rotated in step, right?
Sorry?
It has to be rotated in step, like not slow rotation cannot happen. One, then half turn again.
No, the whole bed is rotating.
Yeah, I'm telling that once adsorption is done, the bed is given a half turn.
No,
Continuous rotation.
the bed is continuously rotating.
So then suppose the partition is like this, and one side is adsorption is happening, and the other side there is a porous link between adsorption and desorption.
So there is a seal actually in between. So that ensures that these gases that is coming out from here, they do not leak from there.
The seal is through the bed.
Through the bed, so that it is not actually coming to the other side.
After one side, suppose red side flue gas inlet,
Right.
then it has to have a 180-degree sudden rotation.
So this comes here, so the bed is rotating. So the moment this enters the adsorption range, these are partitioned, right? So there is a seal there. So as a result of that, the moment it enters here, it comes in contact with the flue gas, right? And then it keeps loading. Here, the moment it comes out from here, it does not come in contact. There is no contact with the flue gas anymore. Then it comes to the desorption. Again, we are just showing it for the cartoon. We are just showing it only adsorption, desorption, but you could have other step. But the moment it comes here, it comes with steam. So then come in contact with steam, then desorption actually starts. So as it rotates, it dissolve, and then it enters this adsorption section.
The pipe is smaller than this pipe, or pipe is half the diameter.
No, so the collection and other things, these are actually tricky. If you have access to a power plant, I will suggest definitely have a look into it. This is the most common actually, and it's there in the book actually. Any power plant book, you can actually, it's called Lungs type air preheater. I'm sure most of the companies still actually uses them. Very efficient heat recovery.
We have radial flow
So the flow configuration that you could have it's basically for many of these cases, the issue comes from a sealing perspective. So when you have a radial flow, you can have a collection pipe and consider that. But what point you have to remember here is there is something which is rotating. So sealing a rotating bed, these are a lot of practicality issues there. If you can do it, yes, any configuration is actually possible there. But traditionally, these flows in this direction, they are because the seal is along these borders. So you do not need to worry about the seal. But now if you are flowing in this direction, that means then you have to collect it and send it out. And that will be a stagnant location there. That makes it actually, it makes it tricky to have those seal configuration there. So, but yes, if somebody can come up with a mechanical design, you can have any type of a configuration here. Yeah. Yes.
We actually, like we can run the bed in the dynamic operation, then take a snapshot, the last point, and work it as a steady state. So, does that, can we use that same thing, methodology for absorption bed, like for capex and opex calculation in
Yeah, as I was saying that it will be good to read those papers. I will actually suggesting this one. So for that, you have to, the problem here is the last point in the bed is not really sufficient for telling you that how many adsorption bed and desorption bed you will need. So first is that you have to solve to cyclic steady state. Then you have to calculate number of adsorption step and number of adsorbent bed and the desorber bed. That is what you have to do, consider that. And that is what I was saying, you have to solve a scheduling problem that will give you number of adsorber bed and the non-adsorption steps. Sum it up, that gives you the total amount number of bed that is required for the capital cost. That's done separately. That's a different calculation. You can put it in ACM as a scheduling problem, but we generally do it separately. And the steam flow rate and all of this is integrated over time. So how much steam you needed for the desorption, through the entire desorption cycle, you integrate that. That's the total amount of the steam that you need. So those are all time integrated values, and then there are these capital costs that are done separately, and that is how it is done. Yeah, so I will say that like those papers which has got the economic analysis, we try to explain that how this type of things should be costed. Yeah, Dr. Sapnil.
Is the adsorption half of the bed is also segmented like pieces of pie? I mean, physically divided? Because if the whole top of this adsorption bed is available for few inlets, what stops it from, say, entering from 0 to say pi by 4 radian?
Right. So there are two, this is an interesting question. So if you really think about it carefully, what you will notice here is there are two things. Yes, one is the distribution. The other thing is that if this is the same flue gas coming in this direction, this has got at the top of this section, it all has got say 10% CO2. But this flue gas that goes through here, it is coming in contact with the solid sorbent which is already loaded, right? So what you really do not want it to be there a lot of flow coming through here, because if that goes there, then it is already coming with respect to the loaded sorbent, so there is not much opportunity for doing that. So this is a distribution problem. So it is possible to do a non-uniform distribution. You can also consider a uniform distributions and all of those. But for CO2 capture, it is possible to have, because what it actually do not show up here is that there is a distributor at the top of it. And that comes from the distribution systems there, how you like to design it. If you say front portion should get more flow rate, later portion not much. This is that you can actually incorporate it that way. Okay, any other question here for this rotary bed?
Yes, there is one online participant. There is one question. So he's asking what is the life of sorbent and after how many years do I need to change?
Yeah. So yeah, that's actually a really good question. So if you see my slides, actually a couple of slides later, I have some studies that I will be discussing there. So I'll probably answer these questions around that time and go into more details. But that's actually a very important question that we all need to consider for economics of it. But we did actually look into that and analyzed it. And I will also give my perspective of what should be done for other absorbents here. Is there any other question? Any other questions from the room here?
Here, flue gas
Uh-huh.
normally consists some small minor micron level solid particles, carbon in terms of solid particles and also carbon in terms of gases of forming CO2 gas and kind of. Here when we are using carbon steam, first question is why we are using steam? Because steam means clear different pressures. Like when the pressure goes up, again the pressure, the superator steam will be there. What type of steam we have to use it? Here steam from the carbon just as capturing solid particle also, as well as gas is carbon particle also. Now, again the percentage of capturing CO2, both solid and gases, whether it's steam is effective or some other carbon we can go directly instead of using steam. Because again the steam will go out along with CO2, leaving the solid particles inside the one. So when it's left the solid particle inside this carbon state, when you come to the enter into the absorption state, again the diffusion will decrease because already it's loaded. Without removing the steam, already carbon particles stick with that surface.
Okay.
So whether how effective we are going to remove all this.
That's actually a very good comment. So the first thing I would like to mention here is that all capture processes has a pre-processing step. So you really, irrespective of whether you are using a solvent or a sorbent, you really do not want to send any kind of a solids loaded into the gas into the system. You must take it out. So what are the technologies people use? So yesterday, I probably do not have that anymore here, but yeah, during actually my seminar, I presented that. So I showed some of the pre-processing steps. One of the important one is the DCC, direct contact cooler. So this is actually water sprays. So this water actually takes out a lot of the solids present in the system. This issue is there for when you are treating for the coal-fired power plant, because that gas has got the ash and the solids and all of that. Depending on the technology and the country that you are talking about, there is always a suspended particulate matter emission standard that you are following. So you are already probably considering an ESP like electrostatic precipitators, water scrubbers, and things like that. For these systems, including solvents, not for sorbents even, including solvents, there are other filters people use. There are ceramic filters which are used, and then I know in TCM, they installed, because they use the RFCC regenerator gas. So RFCC regenerator gas has got catalyst fines in it, and it's very difficult to separate it. So they have, you can read this one, it's called a Brownian motion filter. That actually takes it out, most of the particles out. You should not send any of the solids to the bed. Yeah. I'm not sure you are familiar with like many of the refining technologies where the reactors, at the top of the reactors, most reactors has got a filter actually at the cage type of filter, and maybe two fine layers, and during shutdown, people will take out those filters and outside because there are some unknown material. It's not expected to show up, but it will show up. And then you take it out because you do not want to get it into the catalyst bed there. Once it gets into the catalyst bed, it's a difficult problem for you to solve. So you have to take it out before it enters the bed. Any other question?
So, general value of the tons of adsorbent required
there is really, you have to calculate it. So basically, if you see this design, so this tells you, like when we do this design, that actually tells you the number. So if you look into, like for example, right. So you see that this bed design, I have first provided the bed design. Oh, I did not. I thought at some place I gave that. Again, probably have to look into. Yeah, we have that here. Okay. So if you look into that, like that one bed has got, axial bed has got this, and then it has got radial flow bed has got this and this. This tells you the volume. Right. That, and then it tells you how many total beds you have. So you multiply it by that, and then you multiply that by, so this is the volume, and then that multiplied by 1 minus epsilon, the bed voidage. That gives you the solid, and then you multiply that times the density of the solid. Right? That's the bulk density of the solid that you have there, and then when you give that, that will give you the mass. So
For the power plant system, the example that you have mentioned, in that case, like what was the flow rate that you're taking and what was the material?
yeah, I cannot exactly give you the number at the top of my head, but these are also given in the in our papers actually. It gives you the total amount of flue gas. It has got multiple cases like pulverized coal plant, subcritical, supercritical, natural gas combined cycle plant, and then individually it gives the flow rate and also all these numbers actually. Okay. Any other question? Okay, so moving on. The other thing that is, which is very important, so far we talked about the fixed bed systems. What is the biggest issue with the fixed bed system? Pressure drop, okay. Right, concentration, because we have a fixed material there. Other? Heat. This is one of the biggest things. Like remember I said, oh sorry, I deleted that. I said the sensible heat. Because every time you are heating up the solid, in a typical system, that's why people like, in many cases, the pressure swing adsorption. Like you decrease the pressure. Yes, compressor takes the load, but here what we are saying that if you have to heat it up the entire amount of the solid, that may require you quite a bit of heat. If you are now saying, I want to regenerate every 10 minutes or every half an hour or every 45 minutes, that means that every 45 minutes you are heating up the bed. So you need an effective heating system and also that amount of heat there. And that actually hurts these beds. And all our calculation shows that basically, given the amount of CO2 that you have in the flue gas and the large amount of the flue gas that you want to process, it's unavoidable to regenerate it like at a longer time frame. You cannot have it like saying, okay, let it be for 10 hours sitting there, a single bed adsorbing, then you will require you thousands of parallel bed if you want to do that. That's not practical or not cost effective. But if you want to regenerate it, you saw that all the adsorption time, desorption time, all these calculations, right? Maybe we can go to this one. Yeah, you see that adsorption time and the desorption time for each one of them. So if you are saying I have got these 360 and like it's about 1 hour that I'm keeping, so after 1 hour I have to desorb. So you are heating it up every 1 hour. This is the biggest issue. Recovering that heat is very difficult because it's a dynamic process, right? So yeah, we had in our paper we came up with some conceptual idea. I'm not sure how much practical it is, but somebody in the industry may actually try those. But one way of handling these is basically having a moving bed model. So in the moving bed model, what happens here is solid comes in and then it flows through the bed, right? And the advantage of this is that because the solids moves, you can take the solid elsewhere and do the heat recovery. And then it go to the regenerator, and then it comes out from the regenerator, and then you do the heat recovery, most like solvent. So once it is in the moving bed regime, it is like a condition where it will flow through the system, right? And so this is a concept, and I keep forgetting the name of this. UOP is, I think, this is really probably one of the very commercial flagship process. They have a name for it actually. It's for petroleum upgrading. Sorry? FCC is a fluidized and circulating fluidized bed, and the moving bed is, I will find it. No, RFCC is still in bubbling and circulating fluidized bed. This one is a moving bed. It's a petroleum upgrading schemes. I think it's for actually increasing this octane number, like that is what is came up with that technology. Yeah, it's a UOP proprietary technology actually. That's a moving bed. That's probably the highest commercial technology that do exist here. So now the thing is that these bed, it's almost treated like a liquid gas system because it will flow through the system, right? So that basically means is I could have an heat exchanger sitting here and all of that. So without going into the model much and all of those, this has got a somewhat of a different heat transfer coefficients and overall solid to gas, but I will kind of avoid all of those things, and basically shows that what you find out, and we consider fixed bed, moving bed, fixed bed for each one of them. But I will again do some cost analysis and did some cost analysis with respect to this. So I will say let's look into some of the cost number, and I know there are some questions about the cost of the materials and the sensitivity to it. So first I will go with the fixed bed, and then I will show you for the moving bed. So for the fixed bed, what we found there, if this is the MEA process, many of these fixed bed that which we considered, if you do not consider any of the heating and cooling processes, right, those embedded heaters and systems like that, this will not be cost effective with respect to MEA. Then we consider that modified process, like which we basically say that we have a heating and cooling that brought it closer to the MEA but still could not beat it. Then idea is that because of the heat recovery, remember for an solvent based systems like MEA based systems, it's almost 85 to 90% heat in the hot solvent is actually recovered. And that is why you save money actually. That is a very large amount of sensible heat for heating up the solvent or the adsorbent for taking it to the regeneration temperature, right? So what you do here is, if you could do a similar amount of heat recovery, this is hypothetical, we are not saying that this is possible, but if you are able to do it, then you could actually beat MEA. For this particular adsorbent, it really depends. The other thing what you have to look into is the sensitivity of metal organic framework price. So here we looked into that. So what is the actual price? So I know there was an online questions about that as well, and many of you really also asked me this question. So the first thing what you have to really remember is that cost we are talking about here is that I buy 1 kg or I buy 10,000 kg. The price is going to be different. So for a bulk production, what's the price is expected to be? You need to really consult the manufacturers for doing that. So based on this metal organic framework, this functionalized metal organic framework, we did actually bunch of analysis. So one of the analysis that you can do and is if you're not familiar with this approach, we can talk about that. It's called the bottom-up approach. Takes into account manufacturing costs associated with each step. So you basically say, okay, in the lab scale or in a commercial case, what are the steps involved, and you decompose it and go by the cost of it. This is involved, but it will give you an idea, and then at the top of it, you consider some markup prices like profit and all of those things. But it will give you what is the bare bone cost is expected to be without considering those approaches. So we did that, and we thought the price will be with all of those, with the current price will be somewhere around $15 per kg. Then as we consulted with the industry and basically said, well, what do you think this MOP prices is expected to go down if I'm actually buying, say, 10,000 kg of these? So what would be the price there? They basically think that it will be somewhere between $5 to $10 per kg without really producing that. It's difficult to know. So this is actually your uncertainty range. So we thought to do sensitivity with respect to this entire range here. So one is free, like somebody say, oh, $0 per kg. And then another one is say, with all these sensitivity prices here. And you see that when, for this particular case, if I'm doing this 35% heat recovery, even only at $0 per kg, it can beat MEA for this one. So what I'm saying here is that as you are developing your adsorbent and new ideas, these are the type of analysis that we really need to do. You have to get the uncertainty in the pricing range. I also have the number of years, so I'll show you that. But these are the type of uncertainty you have to kind of consider there. I think for the moving bed, we did that actually. Yeah, for the moving bed, we did that. Then we talked about the moving bed process here. This one actually shows you a moving bed. So this is adsorption. This shows you the whole schematic of what happens in the moving bed process, because you need whole thing for doing the cost analysis. Just doing the adsorption is not sufficient enough. So you have this moving bed, and then this is where the capture takes place. Then it gets pneumatically transported, and you have the preheat exchanger, then another moving bed where the desorption is taking place. So this is actually the motive fluid is a hot water that is actually circulating, the steam that is circulating through the system, and then we recover the heat and then provide additional steam here, and then once the heat recovery is done, then it is transported back again. So this is the overall conceptual process. Can this be done commercially? Yes. Even though they actually stack this, like the only process that I do know that where they have actually manufactured this and testing this and also tested this, these are actually kind of stacked at the top of each other. So it's a single one that actually helps them. So it's a multiple segment, and so everything comes at the bottom, and then they transport it at the top. This pneumatic transport is generally very standard, always has been used for solid transport. But instead of having at multiple places, you just have it at once, and all these beds you can stack at the top, bottom of each other. So they found commercially that made more sense. Okay, so this one also I did not discuss this, and I will tell you a software. Now whatever we discussed here is that we said SEM is by itself on its own, but if you want to communicate with a third-party software, you say, I have MATLAB, some code sitting in MATLAB, I want to use it. I have some code in Excel, I want to calculate it. I have some optimization that I want to do, and SEM, I'm not able to do it. Then actually, as part of one of the projects that which we worked on, this was a project many years we have been working as part of US Department of Energy. There is a tool set, I'll go over that one. There is one tool called Focus. This software has the capability of connecting multiple softwares. You can have a CFD software, you can have a Aspen software, you can connect it. You have a MATLAB, ACM, you can connect it. MATLAB, Aspen Plus, you can connect it. So multiple software, this gives you the capability to talk between multiple software. So that is what we did this optimization here. As part of this, there are two things that we wanted to do here. So basically, as I was saying, two aspects that we need to consider. So one is the particle lifespan, or we say particle lifespan, this material lifespan, and the MOF price. These numbers that which we consider is somewhere saying that when we were said that maybe it will be 5 to 10, we basically wanted to take a cushion here about 15. So our best guess for these systems is perhaps somewhere about 15 and 2. So that means 2 years lifespan and 15 years, and the worst case is basically saying that this is 30 and this. So case 3 has to be treated as like a worst case scenario, and obviously we can consider this case 4 as the best case scenario. So this type of, for the cost uncertainty, this is probably the best you can do, but ideally what you really need to do it is to run these systems to establish their lifespan, how much activity we are losing over the period of time, and whether that can help you to calculate the lifespan of these materials. So if you do that, then what you do is, this shows you the sensitivity over here. You see in the case 1, case 4, right? These are the one that which, so if you look into the case 1 and case 4, this is $0.50 per kg, right? Obviously, this will be the best option that you can consider here, that you can see. When you consider the $15 per kg, and then if it is 6 months, then you run out of economics. So $15, if the cost must be $15 per kg, then it should be able to survive for 2 years. And then even if you go for $30 per kg, if your lifespan is 6 months, it will not work out. So this type of things also give you a research target. It basically says, if my solid absorbent must cost, or it cannot be cheaper than $30 or $15, that tells you what should be the desired lifespan of that absorbent. So there is, these things actually conflict with each other. You can go for a cheaper one, but in that case, there is not much of a difference, 6 months versus 2 years. If you go for the costly one, you see the differences actually keep increasing, right? And so this is the main thing, takeaway message, that as the MOF price or the material price keeps increasing, the relative differences on the economics due to the lifespan will keep increasing. Okay? Yeah, and this shows you the capital cost and all of those things. Okay, any question here? I know there are these questions. I know there was this online question, and I wanted to wait for this particular slide. So please, whoever asked that question online, let me know whether it answers your questions or not. Feel free to put in the chat, please. Then, yeah, so this is also, we consider this NGCC-based capture, and it keeps doing that. Yeah, so I said that this focus tool connects through multiple software. So in this case, we directly do not use focus to Aspen. We did focus, Excel, Aspen, right? So this is Aspen Custom Modeler. If you want to connect Aspen Custom Modeler to any other software, this tool will actually let you do that. Directly, it is difficult to connect. To do that actually. There is also a Python interface. The focus is all developed in Python. So if you do Python model, anything, this is straightforward connect actually. This is the easiest thing to connect through a Python model. But all the documentations are there. I'll show you where you can find more into this one. Again, we did this cost analysis, different regeneration processes and all of that. And here it basically says that we also looked into the MOP prices for each one of them over here. And again, it shows you that if you only consider, this considers a half a year of time that you have over here and a lifespan. So in that case, you cannot beat actually those MEA baseline studies. So when you develop the adsorbent, having a longer lifetime of its activity is actually very crucial to say that I should be able to sustain for a couple of years. For all these values, like you can take these numbers, like I'm not sure how much your adsorbent will cost, but it will give you an idea about where do you compare with respect to these numbers. Okay. I'll change gear. Anybody has any questions so far for the moving bed and for all this economic analysis studies? Yes.
Doesn't the solid attrition from the solvents create problems? Or because like, or you have to like keep it in a like a fluidized regime for the moving bed.
So typical moving bed regime is like where you have the minimum fluidization velocity. Generally, it kept about 2 to 3 times of that. When you go to the bubbling fluidized bed, it goes to about 10 to 12 times. When you go to the circulating fluidized bed regime, it can go up to 20 to 30 times. That is where the trouble comes. So up to about 2 to 3 times of the minimum fluidization regime. Most cases, of course, there is some attrition resistance that is expected, but the particle-particle collision is not that prominent in this moving bed regime. That is one of the reasons that we will like these moving beds. But the advantage of that is that you can get a perfect counter current configuration with the moving bed. Okay. Professor L.S. Fan from Ohio State University has got a lot of papers on moving bed, chemical looping combustion systems and others. So if you are familiar with the CLC literature, chemical looping combustions, yeah, including we have also papers with his group and all of that. But he has a commercial system. I do know BMW has got a moving bed combustor for the power plant systems and also for CO2 capture. So a lot of those areas there has been a lot of work there. Yeah.
So then, can in the can we actually account for that material loss?
Oh, yeah, absolutely. Yeah, I'll show you actually all the code that are there. This code that I'm just describing, everything is public actually. I'll show you where those code exist. You can download, play with it, modify it, and whatever it is. Some of these codes are actually, it will show you all the syntaxes of Aspen Custom Modeler. You can just download the code and you modify for your case. If you have a different adsorbent, change the kinetics, change the isotherm, and then you can just use it. Yeah, these are all public domain actually. Okay. This is the last one, the bubbling fluidized bed model. So bubbling fluidized bed, the advantage of bubbling beds is that excellent heat transfer. So if your problem is that there is a temperature rise immediately after the bed enters the system, then the bubbling fluidized beds actually help you. So if you are heat transfer limited and not mass transfer limited, then bubbling fluidized beds will be an excellent option for you to look into. So remember, once again, I will note here is that each type of bed gives you some advantages. So moving bed, that which we talked about. So if you compare all type of bed, right, fixed bed, moving bed, and bubbling fluidized bed, so heat recovery, very difficult. I will not say impossible, but it's very difficult. Yes, yes. counter current configuration? No. Yes. No. So do not get confused with this when we say counter current configuration. Remember, like in a fixed bed system, what we are basically saying here is that if I have something like that and it enters here, this solid is static. If I could actually move the solid in the opposite direction, then that will give me the counter current configuration. Remember, we always, from all our chemical engineering principle, the counter current gives us the best driving force. That's why absorption, distillation towers, absorption, it's all counter current. The heat exchangers, we basically say counter current that gives you the best heat recovery that you could get there, right? So, but because this guy is fixed, you cannot actually achieve it. But this moving bed, yes, you can do it because the solids comes at the top and it flows, and this gas flows from the bottom actually. So, because you can get a counter current flow there, that's what I say. Yes, the bubbling fluidized bed, because the beds are actually in so much agitated, you cannot really achieve these ones. But if you for, I will say, best for heat transfer limited system, no. This could be, maybe, this is yes. And for the mass transfer, I will not write anything actually, because it depends upon where the mass transfer shows up. If it is within the particle level, then doing the fluidized bed will not help you. If it is for the bulk side, then or moving bed or the fluidized bed can actually, the issue with the fluidized bed is that the driving force is actually completely gone. It's the difference between the CSTR and PFR. So you lose the driving force. And whether the fixed bed versus the moving bed helps, moving bed have a definitely higher mass transfer coefficient, but that is, remember that what Professor Sridhar's lecture there, like when you consider the mass transfer coefficient, there are two mass transfer coefficients that which we are talking about, right? One is external, so that is interparticle and intraparticle, right? So if it is the interparticle, that mass transfer resistances will be reduced by using the moving bed. But if the mass transfer resistance is within the particle, there is really nothing you can do. In that case, you have to design the particle accordingly, or reduce the particle size, or do something from that perspective to reduce the internal resistance. Okay, nevertheless, I just wanted to show you this one is a little crazy model, I will say, pretty involved. We consider a 3-region model: bubble, emulsion, and cloud wake region. If you are actually familiar with this type of a system, this comes straight from Cooney and Levenspiel. These are the two papers we have here, like Andrew Lee and David Miller. These are our collaborators also. So we started with that model, and then Srinivas Modekutti, he actually did develop this model for the dynamics there. So this is how it works. It actually exchanges between all these regions. These are the bubble region equations, and it has got many more terms here. And then these are bubble region gaseous component, cloud wake region. These are other things: concentration, the energy balance equations, cloud wake region, similar equations here. Then we have the emulsion region, the similar equation over here. Then there are adsorbed species equations for energy balances. Then we have the hydrodynamic model. These hydrodynamics models for these systems are actually pretty involved, so which we considered here. Then we have the reaction kinetics model, and then it shows you the overall system over here. So this has got a fluidized bubbling, fluidized bed, followed by a moving bed. So previous one that I show, moving bed, you could have a bubbling fluidized bed, moving bed, that combination that you can consider. It also has all the heat recovery and all those stuff over here. And finally, I will say, yeah, you can look into this. These are all from our paper here. This also gives you a decomposition of all of these. So where the solid adsorbent is helpful is here, right? Basically, compared to MEA versus these, or like the liquid versus the solid adsorbent, the advantage there is that you do not have this part you can save, but the sensitive heat and this one, that can be pretty close. Like this guy, if you are not able to recover it, it is actually can be very difficult. So even though there is a good bit of a sensible heat here, you can actually recover it. So this is under some ideal situation that you have there. So what I will say is that for solid adsorbent based capture, selection of optimal contactor technology is absolutely crucial. And you would like to go to close to the isotherm if you can do it. This is the best thing you need. So for doing that, 3 things important. Deciding the type of the contactor technology, deciding the design of that, and deciding the operating conditions. You should optimize all of these. If you really want to do a good job and basically say, my technology is the best, then this will be absolutely crucial to do all of that. Right? And that will tell you that what is the best economics that I can get here. I would also suggest the economic analysis with quantified uncertainties, like you saw those uncertainties that which we did there, like basically saying this is the lifespan of the adsorbent, this is the dollar value or the INR value of my adsorbent. So what is the uncertainty in my economics? Am I going to take the risk? If my lifespan is like half a year, in real life it goes down to 3 months. If I'm already going down the roof, then that does not will be helping me. So the question is how much risk you would like to cover as part of this one. So that's important when you are doing the economic analysis. But if your economic analysis shows that even if it is half a year and you are confident that your adsorbent will last for 1 year, and you say, okay, even with half a year my economics works out, then your risk is actually very low for that. So those analysis, this quantified uncertainty is actually very important for this economic analysis, because this is a new technology that is coming. This is a standard approach for developing any new technology to evaluate the overall risk. For, oops, sorry, this animation was not right. Okay, so I have some suggested reads. This is from our group, and but there are many excellent papers in the literature, which I will say, please go through it. And for many of the papers that which we have, we also, when permitted, we also upload the code. Like a lot of Python code, ACM code, GPROMS code, you will see on the GitHub that we have there, so that you can download and utilize it. And I'll show you the GitHub page for doing that actually. But these are axial flow bed, the key papers that gives you pretty much all the modeling, all the cycle setup, adsorption, desorption cycle, economics, optimizations, and cover. There is a lot of coverage, including isotherm model and all of that. So it's a full span of systems giving an overall thing. So this is axial flow. Radial flow, my student Anna Monteiro, she just published this paper end of last year, so it is now published. But this is the first one considering this radial flow bed. She also wrote another paper that which has industrial collaboration. So once we get the approval from them, we'll be publishing those. It has some pilot plant test run data from Technology Center Mongstad. So if we get the approval, we'll publish that too. Moving bed paper, original paper, Gautam Kotam Reddy, he developed one of the first ones here, and Srinivas Rao, they are one of the first ones that developed these moving bed models, and then Ryan and Dyson, they expanded all of those, but there are actually a bunch of papers in the moving bed that where we keep extending the models and enhancing the model. You will see a lot of thing that which we tried to do in terms of the heat transfer coefficient, not very well understood. Cooney and Levenspield's book goes very well deep into the typical bubbling fluidized bed and circulating fluidized bed. Moving bed, there are not much papers there actually. So we had a lot of conceptual idea about how the heat transfer might take place and all of those things. So you will see these ones. Oops. Okay. Bubbling fluidized bed, again Srinivas Murekuti did the first paper, and then overall theme I will also suggest that this paper a couple of years back, where I and Dr. David Miller from US Department of Energy, we did kind of, this is not a review paper, even though we say review, this is a lot of conceptual ideas actually. Once you open it up, you will see lot of different configurations that which we tried to propose. Some configuration do exist in the literature, some we tried to conceptualize that how this bed might be arranged and all of that. You will see a lot of those for solvent and absorbent, different configurations. I also wrote another paper on this, which is hybrid processes. This was for membrane solvent, but you can think of this as a membrane absorbent or solvent absorbent or many other hybrid processes that you can think about. Like it's basically saying how to synergistically connect those. And finally, these models, if you go under this, if you click this one, okay, if you click this one, I will see if I actually can do it over here. So this is in the public domain. This was because it was it's US Department of Energy. This is also uncertainty evaluation. This also gives you to do that. If you're working in the CFD area, there are a bunch of CFD code for CO2 capture here. Most of these are actually developed using MFIX, so you can actually see the equations and everything there. I don't think there is anything in Fluent or OpenFOAM. I know there was some project, but that was probably not here. And then this is advanced process control. All our models that which we are talking about is actually here in the process models bundle. So if you click on the process models bundle, this is most of the thing that which I actually discussed there. A lot of these are, so if you look into it, we have the solvents. So these are all MEA and all of these things. I just quickly go over these. This is also all developed by this is my student, Josh Morgan and Anderson is all of these things, and this one is Paul Akula. Then the solid absorbent, all of these are these VFB reactors. So if you look into all the bubbling fluidized bed and this moving bed, this was also based on that. And the thing which I did there was the integrated capture that I said, that you come here and all the SEM files are here. If you same model also implemented in GPROMs. If you look into the integrated model, it gives you everything. Like if you look into this integrated model, and I'm not sure it will open up if I do this. Yeah, it will not probably open up. Maybe I'll see if it does. Perhaps we cannot see it here. Oh, it did actually. Okay, wonderful. Let me see if it opens up. Okay, oh, this is good actually. So this connects you, if you ever run into SEM syntax error, I will say look into here. This is called all kind of syntaxing that we had to use, because I showed you the equations for the bubbling fluidized bed and moving bed. These are actually very complicated models there. And it also shows you how to connect multiple equipment items, and you come up with your overall thing. Okay, So if you look into here, this is all built in SEM, and zoom in, and all of that. Okay. So this has got many equipment items. You will see if you use these, it will show you all of these processes that which you consider, including it has got the also the CO2 capture and all of these things, including this is the entire process that which you consider. These bubbling beds that which I was actually talking about, sitting here at the corner, these are like the two-stage bubbling beds if you want to see this. So the way to understand which model goes where, if you bring it here, remember it is showing you, notice what it shows you. Within the parenthesis, it says BFB. So that is the model that it is actually using. You come up under the custom modeling, you go to the models. So all these models actually we developed as part of this, right? So if you now go to the BFB model and you see this model, so this is the BFB model code. So it gives you a lot of, so you see the declaration of the parameters itself actually is very long. So these are all differential variables, all these distribution, everything that we show as a distribution 1D is the differential variables and whatever. And so you see the declaration itself is actually quite a bit. That basically tells you that a lot of things actually involved as part of these ones. So I will say if you ever run into any issues into syntaxing and structure, do this. And this also has, I briefly said that you need to initialize for complicated model, otherwise it will not work. So these ones are actually has also an initialization. It has a rigorous off and all of those things. These things are actually done from a different task manager perspective. So all these equations are actually here. I will encourage you to look into it if you are interested. And here, yeah, so overall, that is where I wanted to end. Sorry, the script. No, we have this. I think that is all that you will actually need this as part of this. So here you have got all the CO2 compressor also, everything. The heat exchanger model, mixture models, splitter models, valve models that which we developed. So everything that I said about the pneumatic conveying and everything, that is all included. This is just actually a little bit of a gigantic model, but it shows you that you can do exactly the same thing with AdSim. So if you are using AdSim block will be one here, and then everything else you can bring in other things. Okay, so I will stop here and say anybody has any questions. It's 12. Okay, so seems like we are good here, and if you run into any trouble in writing the code or anything, let me know. And one more thing which I discussed with Professor Palla here is that I will actually upload the desorption slides and the cycle setup. Give me a week time when I go back in one of the weekends. I'll just put together those slides and step-by-step approach if you are interested to do the entire cycle within AdSim. The other one where I said that you write your own code and do the cycling and all of those are a bit tricky. But within AdSim, those things can actually be set up. Okay, very good. Okay, thanks everybody.
Thank you, Debanshu. So